Hello, this is Seth Hemingway from the Office of Compliance's Water Branch. I am here with my colleagues Jake Wynn and Laura Paradise, who are operating the webinar. Welcome to the re-recording of Troubleshooting Noncompliance at the Smallest Wastewater Treatment Plants, Part 1, Ohio's Package Plant Initiative, covering nutrient conversion. This webinar, which was originally broadcast on October 17th, 2019. This is part of EPA's Office of Compliance's Technical Assistance Webinar Series for plant operators, inspectors, and compliance assistance providers. These webinars support the NPDES Significant Noncompliance, or SNC, Reduction National Compliance Initiative. The goal of the initiative is to reduce noncompliance among Clean Water Act NPDES permitted facilities. While our focus is on helping wastewater system operators return their facilities to compliance, the webinar should be equally valuable to operators who are interested in fine-tuning their systems. This and the remaining webinars are focused specifically on issues that arise at small wastewater treatment systems and will be presented by John Van Domelen from Ohio EPA's Compliance Assistance Unit. Check with your supervisor to determine if you can receive continuing education credits. Viewers should also be aware that they should get the flow chart from Ohio's Activated Sludge Process Control and Troubleshooting Training Manual to follow along with the presentation. I have a very quick disclaimer. The information presented in this webinar is intended as training to help NPDES regulated entities and NPDES regulators understand additional techniques that can help operators refine their operations and, if needed, to help bring them back into compliance. Invited speakers are not speaking on behalf of EPA and do not necessarily reflect EPA's positions or policy. This webinar is not intended and cannot be relied upon to create any rights, substantive or procedural, enforceable by any party in litigation with the United States. EPA reserves the right to act at variance with the information presented in this webinar at any time without public notice. Today we are lucky to have John Van Domelen as our featured speaker. John has worked for Ohio EPA for 25 years. He spent the first 6 years reviewing detailed plans and issuing permits for new wastewater treatment plants and collection systems. He eventually joined the Compliance Assistance Unit, where he has worked for a total of 19 years troubleshooting noncompliance at wastewater treatment plants, ranging in size from 1,500 gallon per day package plants up to 15 million gallon per day municipal systems. In addition, John has trained operators of wastewater treatment plants in process control of activated sludge, microbiology, biological nutrient removal, among other topics related to wastewater treatment. He has also presented at the West Tech 3 times, at many Operator Training Committee of Ohio and Ohio Water Environment Association workshops, as well as for other regional, state, and local organizations. He has published articles pertaining to topics of interest to operators in the Buckeye Bulletin, a publication of the Ohio Water Environment Association. John graduated from Ohio State University with a Bachelor of Science in Civil Engineering and is a registered professional engineer in the state of Ohio. His wife tells people that no one should have as much fun at his job as John does. Clearly, John has seen a lot and knows what he's talking about. Following his presentation, which will run about 75 minutes, John will respond to many of the questions that were posed during the original broadcast. So thank you, John. Take it away.
Okay, thank you, Seth. Again, I am John Van Domelen. I work for Ohio EPA in the Compliance Assistance Unit. I've been working here, as Seth said, for about 25 years, and what I do is I go to treatment systems to figure out why they are in non-compliance with their NPDES permits. The Compliance Assistance Unit was created through the Clean Water Act in Section 104G1 of the Clean Water Act, to be specific. In Ohio, this grant was used not for an FTE, but rather used for equipment and supplies, travel, and training for us. In the positions, the FTEs were funded through normal revenue streams, which is a little bit different than what a lot of other states did. They funded the FTE, but then there was no money for tools or anything else. But most importantly, the Compliance Assistance Unit had great support from the management at Ohio EPA. Again, what we do, we provide on-site technical assistance to communities. Again, we'll go any place, public, private, whatever. But we've gone to plants as small as 1,500 gallons per day up to and exceeding 15 million gallons per day design capacities. And what we do is we help operators to overcome non-compliance with their NPDES permits. We troubleshoot all aspects of wastewater treatment, you know, from I&I stuff to conversion and separation to disinfection. But what we do is we don't guess, we measure. And we do this we get them back into compliance through process optimization of activated sludge using some cheap, easy, and effective process control tools. Cheap because no one has any money, easy because if it's hard, no one's going to do it, and effective because if it isn't effective, why bother? So what we did was we created the activated sludge process control and troubleshooting manual and chart. So we started off with the flow chart, which catalogs all the conversion issues and separation issues that will probably crop up and cause maybe 95% of all significant noncompliance with effluent limits. And then we built the manual to go along with the flow chart. The package plan initiative was something that we did in Ohio back in about 2014, and the director of the Ohio EPA at the time tasked the Compliance Assistance Unit with trying to solve significant noncompliance in small wastewater treatment plants in Ohio. So what we did was we focused on the design capacities of less than 100,000 gallons a day design flows, and we focused on mechanical systems. We didn't do lagoon systems because they are much different than mechanical systems, and our expertise was really in mechanical activated sludge systems. When we did the package plan initiative, we got a grant to buy cheap, easy, and effective tools and give them to the NPDES permit holders that were invited to the workshops that we staged. What we reasoned that if we could get the operators to do process control, real process control, we believe that we could solve significant noncompliance through this type of data collection and interpretation of that data collection, resulting in process optimization. There I am demonstrating to a small group that was invited. But anyway, what we did was we invited just the plants in significant noncompliance to these workshops. We gave them the tools, the cheap tools, the expensive tools. We bought about 40 of the expensive tools and set up lending libraries in the district offices so the operators could have all the tools that we reference or that we use in this presentation. And we gave them the training, and then we went out to treatment plants and demonstrated the tools. The Compliance Assistance Unit really views wastewater treatment from a biological point of view. And by that, what I mean is we measure the physical characteristics, like sedilometers and core samplers, visual characteristics, like just using your eyes and actually your other senses too, smell and listening. But most importantly, what we do is we measure the chemical trails that the bacteria leave behind as they convert the pollutants in wastewater into more bacteria and nitrate and carbon dioxide eventually. Okay? This is a chart that we started with when we were looking at significant noncompliance in Ohio. What it shows is the 5 district offices: Central, Northeast, Northwest, Southeast, Southwest district offices, and the different categories of treatment systems: private, public, semi-public, and specific, which are a catch-all category. And then in the first column, it showed how many, or I guess the second column, it shows how many treatment systems, mechanical treatment systems, less than 100,000 gallons a day, non-lagoon, that were in each district office and in each category. The third column shows how many were in significant non-compliance, and then the last column shows as a percentage of the non-compliance of the total. Okay? And this was some treatment plants that were in significant non-compliance at some time over a 2-year period. Okay, so the world of non-compliance in Ohio. Causes and solutions. Well, basically, I believe there's 3 main reasons for non-compliance, at least with their effluent permit limits. One are operational issues. If the operator doesn't understand basic process control or the basic principles behind wastewater treatment, then we can teach that, okay? Or if there's maintenance issues, we can teach that as well. Oftentimes when I go to a wastewater treatment plant, there are design issues. Something about the design did not provide enough flexibility for the operators to meet whatever comes down the pipe. So if you have a design error or a construction error, then you have to do even more process control. And oftentimes what we end up doing is looking for workarounds to bottlenecks or other design issues. And then the last cause for effluent limit violations and noncompliance is administrative issues. For instance, they don't provide enough staffing for the treatment plant, or they don't provide enough funding for operations and maintenance and replacement. And if the administration is recalcitrant in their responsibilities, then maybe, in my opinion, that's what enforcement's for. That's my opinion. Okay, so let's take a look at some of the plants that I've gone to over the last 20 years. Welcome to my world. Here's a plant that's kind of out in the middle of nowhere, and it actually was not too bad, and it was functional. It doesn't look very pretty, but it was working pretty well, and it didn't take a whole lot of work to get it back into compliance. Here's another plant. Looks like it's suffering from a little maintenance, I guess, groundskeeping. I can tell that there's a wastewater treatment plant in there because I see the blower housing. And if you look just to the left of the blower housing, you see some grading and a little bit of concrete. Well, that's the wastewater treatment plant. But you know, it can be working. Here is one that we went to. This one had some failures of the influent pump, so they bought another pump and tied it into the control panel there. Kind of. If you notice in the background, there's a lot of dead grass around. When the vault chamber there behind the control panel failed, and raw wastewater went all over the ground. So again, I don't go to places that work very well. Here's an oxidation ditch, a little bit bigger plant. They wondered why they had low dissolved oxygen filaments. Well, they were missing probably half of the paddles on their oxidation ditch. You probably would have low dissolved oxygen. Again, another maintenance problem. This is a final clarifier that probably should have been cleaned out months ago. You can see the sludge buildup, which gets skimmed off the top by the bridge there, and then you have all these plants that didn't just pop up yesterday. So when you see a lot of weak maintenance, there's usually some other problems with the plant. Here's a good one. You can tell this one's not going to work. This is the skimmer and the return sludge line from the clarifier back to the aeration tank. We were doing a workshop for a county group, and they picked the treatment plants but didn't go out and inspect them in time, and this is the first one we went to. It was totally non-functional, and probably hadn't been functional for quite some time. This is what the return pipes look like. Obviously, obviously a problem. And this is what the tablet chlorinator looked like. It probably hadn't seen chlorine tablets in months, if not years. It took a little effort to get that top off. Here is a design error. You can always tell operators are some of the most creative people in the world because they can see the problems, but they don't always have the tools to correct those problems. I can't tell you how many times we see bricks, blocks, boards in flow channels trying to fix what is a flow splitting problem. And this is just a typical example. They have their concrete block trying to direct flow more evenly, and they have a spare concrete block ready to go in case something happens to the one that's in the flow channel. Anybody seen the Cardia? Anybody seen the Cardia this bad? This was a pretty bad treatment plant, and it's inside of a house, fortunately, because otherwise they would have Nocardia all over the ground, all over the feet, all over the landscape, but it was all contained by the buildings. But every morning when flow would come in, the 2 feet approximately of Nocardia that was on top of the tank, there was a constriction with flow going out. It would rise up, spill over the tank, and spill on the floor, and the operator would have to clean it up every morning. I like to say that we solved this problem, and they have not had Nocardia literally they haven't had Nocardia since. But they were like, the operator had cleaned up Nocardia foam like that for several years before we got there and helped solve their problem. Here's a little bit bigger clarifier, not a package plant, but
excuse me, John?
Quote, 10 state standards type. Yes.
John, I did want to just remind you that Nocardia, if you want to go ahead and give the solution to that one, because I know that's one that we had a question on.
Sure. Let's go back to the Nocardia picture. One of the questions was, how do you control Nocardia? Well, it took a little bit of research, actually. And one of the main references that I used for that research was, they call it the Jenkins Manual. It's like, I don't have the title with me right now, but it's like how to control solid separation, foaming, and other solid separation issues. But anyway, it's a filament book, and most people just go in and look at the filament pictures and how to identify filaments. But if you go way back in the back of the book, there's a whole section on Nocardia. And what Nocardia really likes is a lower pH. The highest growth rate for Nocardia is between 6 and 6.5 pH. It starts tailing off when you get above 6.5. And once you get up to around 7 pH, it starts going down again. The other thing that causes Nocardia is a long MCRT. So to get rid of Nocardia, you have to waste down to about a 2 or 3 day MCRT, and then don't let it get beyond about an 8-day MCRT. Because once you get past about an 8-day MCRT, then you have the growth condition for Nocardia. The other thing you have to do is if you have foam this bad, you have to suck the foam off. You have to get a pump truck in and get rid of the foam. And you might have to do that multiple times because the Nocardia is growing in the mixed liquor. But because it's hydrophobic, it floats. And then if you aerate floating Nocardia, then you will get foam. So sucking it off. And then finally, this plant had a subsurface takeoff, so that causes foam trapping. And when you trap foam, it doesn't go out. But it accumulates and continues to accumulate. So what this plant did was, first thing they did was suck as much foam off of the top as they could with a vac truck. They they wasted down almost until they lost nitrification, down to about a 3-day MCRT. They augmented the pH in this facility was actually pretty low in the aeration tank. It was about 6.2, so they augmented with sodium bicarbonate to raise the pH. It's a really safe way of doing it. And then they took the subsurface takeoff from this aeration tank and made a surface takeoff. And when all those things came into play, and they used process control methods to do that, their nocardia problems disappeared. It was amazing. And the operator was very pleased because for the first time in several years, he didn't have to clean up nocardia every morning. Okay, let's go on. Welcome to my world. Here is a clarifier that's just about ready to lose all of its solids. Yikes. And here is looks like a sludge drying bed, but actually it's a sand filter that caught a clarifier that lost all of its solids. And that's a lot of solids, and that's a big sand filter. But even worse, if you look to the left at the sand filter beside it, it's flooded. And the sand filter to the right looks like it has a lot of solids built up too. So this is a long-term problem that really, really should be solved. Okay, welcome to my world. I think we solved it. This is a photo. This is a design error at a plant, and the operators, I really can't, I don't even, this one is just so bizarre. There wasn't enough head for the sludge to get to the sludge chamber or something like that. I never did quite get the complete story, but the sludge sort of popped up out of the ground, and then they built this little channel there to direct it to where it was supposed to go. Obvious design error. And then this one is another one. This is a collection system. It was a small diameter collection system that failed from about day one. It was surcharged for, I don't know, 3 or 4 years. And they had 3 engineering firms come in and do ionized studies, and they were all inconclusive. They finally asked us to come in. And again, we came in May, and the whole system was surcharged. And so we couldn't really do a whole lot then. But then what happened was we actually were driving by this plant in late August, and it had been a dry summer, and we thought, wow, let's go check in. So we drove over, popped a manhole, and the manholes were about 25 feet deep, and it was very hard to see. So we took a digital camera with a flash and closed our eyes and took a flash picture, and this is what we got. And we finally figured out why the system was surcharged all the time. As you can see, they have the manhole was cored with a gasket for an 8-inch pipe, but they have I think it's a 4-inch pipe going into it because it's a small diameter gravity system. And the pipe, you can see the pipe bedding, and basically what it is just a French drain all through the town, and it would leak into these manholes. And we found about 15 of the 32 manholes were like this. The rest of them were fine. And once we figured it out, they had the manholes rehabbed, sealed, and the problem disappeared. 3 engineering firms couldn't figure it out. So here are the tools that we use. Up at the top left is in a single parameter colorimeter for ammonia. That's great because it'll give you a number. Below that is a fish kit, an aquarium kit. We call it a fish kit. But uses the same chemistry as the colorimeter above it, but you have to match the color of the liquid after it's reacted to a plate, and it doesn't really give you a very good range. But if the test kit says it's less than 1 milligram per liter, I believe it because I've done side-by-side testing. If it shows it greater than that, it's probably out of compliance. So anyway, the fish kits, pass-fail. The colorimeter is one that will actually give you a number. Besides the colorimeter at the top is an alkalinity test kit. Alkalinity is very important because the nitrifying bacteria uses bicarbonate for its carbon source, and at the pHs that are in aeration tanks usually, well, it is bicarbonate, but when you run out of bicarbonate, the pH will drop and you'll quit nitrifying. Below that is an old YSI 55 DO probe. The DO, that's an older one. Now we have newer ones, but that's one of our tools. Besides those two is the core sampler. Not a great looking core sampler. It looks like you have over 5 feet of solids in that core sampler, but that's how you check what's going on in the bottom of a clarifier. At the top right is a wastewater centrifuge. This is probably the most valuable tool in my truck because I use it for so many things. It's a simple tool, and we'll get into that in a little bit later. And at the bottom right are settleometers to see what the settling characteristics of the biology that you grew in your aeration tank, how they respond. Okay? And here are the tools that work. The settleometers, down at the bottom right, an alkalinity test using the DO probe. Two up to the center right are the centrifuge tubes. You fill it up with a mixed liquor or return sludge, and then in 15 minutes it spins it down so that you can see how many solids are in that sample. Very good tool. The colorimeter down below it shows a 0.2 milligrams per liter of ammonia, and then over on the right is the 5.5 foot sludge blanket that you can't see unless you do a core sampler. Okay? So the solution to all these problems is the flow chart and the training manual. Over the years, we have accumulated all the contents that are in the flow chart and in the manual. We have accumulated those process control methods. And so finally, after about 15 years, we decided to memorialize it in the flow chart, which we made first. And then we wrote the Activated Sludge Process Control and Troubleshooting Manual as a companion to the flow chart. Okay? So, now what I'm going to do is to continue, and we will go through the flow chart and with explanations of each of the boxes that are in the flow chart, and a little overview now of how that flow chart works. Okay, so first off, there are a few basic concepts to wastewater treatment. In your influence, you have water and pollutants, essentially, and those pollutants are CBOD and ammonia, primarily. There are other things in there too, but if it's biodegradable, the bacteria will convert those pollutants into more bacteria, floc and filament, okay? That's a conversion process. And then once the pollutants are converted into bacteria and carbon dioxide and nitrate, then it goes to the clarifier where the second process, separation, occurs. The bacteria is separated from the now pollutant-free water. Throw a little disinfection at it, and you can discharge it back into the receiving stream. Okay? So those are the two big processes that we highlight in the manual: conversion and separation. So let's look at the chart. You start at the top, and what that says is the clarifier effluent ammonia less than 1? Okay? So if it isn't, you go down the left-hand column, which is highlighted in the light blue here, and what that is, those are all the issues that can cause conversion problems. Okay? You have to do conversion first before you can separate it. You can't separate what isn't converted, okay? Now, the other branch, the yellowish branch, is divided in, these are separation issues. This is divided into two branches. There's the middle branch, where you grew the wrong kind of bacteria, mainly filamentous bacteria, which causes settling problems, or the right branch, which addresses clarifier issues, namely hydraulics and return sludge. So those pretty much cover all of the issues that can cause separation problems. So together, you can solve conversion issues and separation issues, okay? So, how do you use it? You begin with box 1, clarifier effluent ammonia is less than 1. If the response is no, you follow to the left the red arrow and go down the separation issues. If the response to the clarifier effluent ammonia question is yes, it is less than 1, then you go follow the green arrows to the right for separation issues, okay? And it follows the same way all through the chart. If you have no, the chart will either ask a question or give you something to do. If the answer to the question is no, you go to the left. If the answer to the question is yes, you go to the right. You apply the corrective actions that it tells you to do, and then you start again, and you keep following the flow chart until you reach compliance, right there. Okay, that's the goal, the green box, compliance. Okay, so let's start at the top. Box 1, clarifier effluent ammonia is less than 1. Okay, why do we do that? Why do we check clarifier effluent ammonia? Well, the conversion process will convert CBOD into bacteria and CO2, will convert the ammonia into nitrate and more bacteria. Okay, but the BOD test takes at least 5 days if you do it yourself. If you're sending it out, it could be 10 days to 2 weeks before you get the result. That's not good enough if you're troubleshooting. Ammonia is an indicator. The nitrifying bacteria are somewhat more sensitive to poor conditions in the aeration tank than the CBOD oxidizers. So when your ammonias are starting to go, you need to do corrections for that. So it's sort of like an early warning system, because, you know, CBOD is easy. Ammonia is a little bit harder. And if you lose, and it's unusual to have high CBODs and low ammonias. Typically, your ammonias will go first, and then your CBODs will follow in violation if you don't correct for the ammonia noncompliance. So, for a mechanical plant, we determine that if you're less than 1 milligram per liter, we figure all mechanical plants should be able to get less than 1 milligram per liter of ammonia. Conversion is complete. If you're greater than 1 milligram per liter, then you probably have a conversion problem or are well on your way to a conversion problem. Okay, so that's that line. We expect all plants to have less than 1 milligram per liter of ammonia leaving the clarifier. Okay, so how do you measure ammonia? Again, here's another colorimeter. This is a Hawk 890. It's a multi-parameter colorimeter. You can do all sorts of chemistries with it, but it will give you a good number. It's good enough for process control. You probably don't want to use it for your permit. It's probably not acceptable, but for process control, it is really, really close to an MPDS permit analytical method. If you can't afford that, because that's pretty pricey, you can get an ammonia fish kit, okay? And again, you can see it's the same chemistry as the colorimeter, but you have to match the color of the reacted sample to that color strip there, and if it's darker than 1, I say all bets are off. So I call that a pass-fail ammonia test. Okay? Okay, so if you look at your chart, we said, okay, the clarifier effluent ammonia is greater than 1, so that takes you, the answer is no, it's not less than 1, so we go to the left. In the next box, box 2 says, is the aeration tank effluent less than 1? Okay, the reason we say that is because there are instances where, well, there's nothing in the clarifier that will remove ammonia. So if the water going into the clarifier is greater than 1, then of course the clarifier effluent ammonia should be greater than 1. So you check the aeration tank ammonia. If the aeration tank ammonia is less than 1, but the clarifier effluent is greater than 1, now we know that the problem is in the clarifier rather than in the aeration tank. Okay? So what can happen? Well, let's look at box 4. What can happen in a clarifier that can release ammonia? Well, look at the scum baffle there. It's right there to the left of that picture. There's lots of solids in that scum baffle. If those solids aren't removed and they just sit there, over time they will start dying, and when bacteria die, or go septic, they release ammonia. So you might have converted the ammonia in the aeration tank, build up solids in the scum baffle, and then the scum baffle starts releasing ammonia back into the clarifier. There's another one. Look at all the solids in that one. It's billowing out of the clarifier, or the center ring of the clarifier, and they're growing plants. What about the clarifier surface? If you see a lot of denitrification or scum entering the clarifier, and you have that layer of scum all over the place, well, that's going to start breaking down, especially in the summertime when it's hot, and it's going to re-release ammonia right by the weir. It could very easily cause a high ammonia in the clarifier. Here's a big plant that has a large surface area full of scum, and again, you can see it billowing out of the center ring of the influent to the clarifier, and the whole surface is covered, and the scum beach is full as well. But again, having all that surface covered with biological foam or biological scum, it can release ammonia. What about a clarifier? There's a core sampler here. Kind of hard to see, but that core sampler is, let's see here, 5, 6, 7, about 8 feet. And they have about a 2 foot of clear on top. If you have 8 feet of sludge in a clarifier, what's going to happen? You're going to have solids breaking down because it's not an aerated environment. And once the nitrate's gone, or all oxygen sources are gone in that sludge blanket, they are going to start to die. And when they die, they release BOD and they release ammonia. Okay? Nothing good happens when you have that much solids in your clarifier. Okay, so let's say the aeration tank ammonia is greater than 1. So now we have to look at temperature. Okay, temperature is important, especially in the wintertime, because when the water temperature in the aeration tank is less than 10 degrees C, the bacteria, including the nitrifying bacteria, will start to slow down. Okay, so as the water temperature drops, you get a slower growth rate of the bacteria, and if you have a slower growth rate, you'll get slower removal or conversion of ammonia to nitrate. Okay, what you see in the picture here is a DO probe, but most DO probes have a thermistor on it. and right there it measures what the temperature is. The temperature in this aeration tank is 7.9 degrees C. You still will nitrify at 7.9, but it will start slowing down. And the colder the water temperature gets, the slower the bacteria will nitrify. Okay? So measure the aeration tank effluent temperature to see how cold it is. Okay, so what if it is cold? What can you do? Well, on a small system, you might be able to take a tank out of service. For instance, if you have high organic loading, the bacteria just metabolizing the ammonia and CBOD will tend to keep the aeration tank, the mixed liquor, warm. But if you have a low organic loading, then the bacteria aren't metabolizing, aren't generating any heat, and the water temperature will continually drop. So if you have a low organic loaded system, you might be able to take a tank out of service if the piping is there. If you have parallel systems, you might be able to take one whole treatment train out of service if you're not bumping up against your design capacity, or you don't have a lot of I&I, because typically you would also take a clarifier out of service. But there are things you can do, because if you can match the amount of online aeration tank to what's coming into the plant, the organic load coming into the plant, then you can obviously cut down on losing temperature to the environment, to the atmosphere. Okay. Another thing you can do is you can use a timer. Okay. Now I'm a big advocate of timers in small systems, because most small systems don't get flow around the clock. I mean, you look at schools, you look at churches, you look at businesses. A lot of times from about 11 o'clock until maybe 6 or 7 or 8 in the morning, they don't get any flow. Okay, so if you're just aerating 24/7, all you're doing, in the wintertime especially, all you're doing is exposing the mixed liquor to the cold air above it. Okay? If you can cycle the air on and off, now, since most of these tanks are buried in the ground, that provides some insulation. You might have a little bit of cold on top, but the rest of the tank is insulated by the ground. But the one thing you have to be careful of, you can't have really long off times. You should bump the air on, maybe just for 15 minutes maybe every hour, just so you can mix the contents and you don't get denitrification in your clarifier, and you can evacuate the clarifier, because most small systems have an airlift pump that will, if you turn the air off, the return sludge quits as well. The other thing you can do is you can cover the tanks. Okay, in this picture, underneath that blue foam insulation, underneath all the bricks, is a wastewater treatment plant. And quite a bit of snow up there, and it looks like they are doing their best to keep whatever heat comes into that plant in the tanks. It works pretty well. Another thing I've seen has been stall mats. I had an operator one time that was having freezing problems, but he was a dairy farmer, and he got stall mats and put it on the grating, and they're about 1 inch thick, heavy rubber, and they're about, I don't know, 4 feet by 6 feet, and it worked perfectly, covered the tanks, and they don't blow away, so you don't need the bricks on top. That worked really well too. You cover your aeration tank, you cover your EQ basin if you can, cover your clarifiers if they have grating on top. Okay? It helps keep the heat. The bacteria will work better. Here is some typical grating that goes over a lot of these package systems, and you can cut fiberglass and just slide it in these channels to keep it from blowing away, and it provides good insulation. Okay, so if it's not, if it's not too cold and you still have high ammonia in your aeration tank, the next thing you need to look at is if you have enough alkalinity. The box 5 says, is your total alkalinity less than 100? Okay, here's the thing about alkalinity. When you convert 1 milligram per liter of ammonia into 1 milligram per liter of nitrate, you consume 7.14 milligrams per liter of alkalinity. Okay? So when your alkalinity gets used up, then you don't have a buffer anymore. Okay? And your nitrifying bacteria won't have a carbon source, so they will quit nitrifying. Okay? Once the alkalinity is used up, the pH will drop like a rock. So if all you're doing is measuring pH, you won't see it. You won't see the alkalinity going away until it's too late. Okay. This is something that I see over and over again since around, I don't know, the early 2000s. Because in Ohio, what we did was they provided a lot of funding to rebuild schools. And in rural communities where they rebuilt new schools to replace the old schools, they had a lot of land owned by the Board of Education, and they usually built it on the same land, and there was a package plant there to take the sewage, and they just tapped the new building into the existing package plant. Problem with that is the plumbing codes changed, and with the advent of low flow fixtures, like for hand washing and toilet flushing, the amount of carry water coming to these wastewater treatment plants has been reduced significantly, like up to maybe 75%. But the ammonia load, they have the same number of students, so the ammonia load is not decreased proportionately. So now you have just as much ammonia, but you have much less carry water, and the alkalinity is in the carry water. Okay? So now, when I would go to a rural school that was having an ammonia issue, first thing I would do would be to check its alkalinity. And more often than not, there was almost no alkalinity in there, and the ammonia was high, and that was the cause. Okay? So, how do you recover for alkalinity? Well, it's one of those cheap test kits. It's a titration. It's an alkalinity test kit. Low range, well, not low range. I guess it's sort of a high range. It goes from 20 to 400, I think. But what you do is you take the aeration tank contents, you let it settle a little bit, and then you fill a little cuvette full of the aeration tank water. You dump it into the bottle. You put a powder pillow in, which is an indicator, and turns the water blue, and then you drop dilute sulfuric acid in and count the drops. Each drop is 20 milligrams per liter of alkalinity. So what you need to do is, see the next picture. Okay, there's a picture. Doesn't show alkalinity, but it does show the pH, and the pH is 5.37 at that plant. But what you do is you measure the ammonia, figure out how much ammonia you have, then you multiply that number. Say you have 12 milligrams per liter of ammonia. You multiply that number by 7, so that would give you 84 milligrams per liter of alkalinity required to oxidize that 12 milligrams per liter of ammonia to nitrate, and then you add 100 to it. So as a buffer, as a safety factor. So you need 184 milligrams per liter of alkalinity. If you only have 100 milligrams per liter of alkalinity, you have a deficit of 84 milligrams per liter. So what do? you add sodium bicarbonate. Okay, here is the fractional amount of versus pH. And as you can see, between about 6.5 and about 10, the dominant form is bicarbonate. Okay, the pink line. Okay, so once you get down below 6.5, then you can see there's not very much bicarbonate left, and it's mostly CO2 forming an acid in the tank. Okay, so that's why you need the 100 buffer. So this is the sodium bicarbonate that I recommend using. It's like Alka-Seltzer for your wastewater treatment plant. It's cheap. A 50-pound bag costs about $15, and it's safe to use. Okay, it's not dangerous. It's not corrosive, neither for the treatment plant nor for the operator. What I recommend is people take some tap water or clarifier effluent in a 5-gallon bucket, about half full. You put a couple coffee can fulls of sodium bicarbonate in it. You stir it up because the stuff isn't very soluble, and then you dump it into your aeration tank. You mix it and dump it in the aeration tank, and then you wait about 15 minutes. You do it while the air is on, and then you take another alkalinity sample and test the alkalinity again. See if you have enough yet. If not, you repeat the process until you have enough. Okay? And then, when you come back the next day, check it again, because you have to see how much is getting consumed. So the goal is, when your ammonia is less than 1, you need 100 milligrams per liter of alkalinity remaining. Okay? Okay, so if it's not too cold, if it's not a lack of alkalinity, it might be a dissolved oxygen issue. Is the aeration tank dissolved oxygen less than 2 milligrams per liter? In the summertime, oxygen is less soluble in warm water than it is in cold water. So a system that might be meeting permit for ammonia in the wintertime might not be meeting it in the summertime if the aeration system is somewhat weak. Okay, so you take your DO probe after you check it out from the lending library at the Ohio EPA district office, and you stick it in the effluent end of the aeration tank, and you see what the DO is. Okay, so if you're just doing a one-time shot, you have to kind of be careful about what's going on in your plant. Did a lot of flow just come in? If so, your DO might be pretty low right there. Did you get there before the flow came in, early in the morning? Well, maybe your DO is really high, but maybe the flow hasn't hit yet and causes it to drop. The other good thing you can do with your DO probe is measure parallel tanks to see if the balance of oxygen is the same in both sides. Oftentimes it is not. In a series of small package plants, modular system, you might have 2 or 3 or 4 aeration tanks. The first tank will almost always have low DO, but as you go to the next tank, it should be higher, and then maybe the last 2, it should be very high. If not, then maybe you have an aeration problem. Okay, so what kind of aeration problems can you have? Well, here's one. This is a bigger plant. This is an oxidation ditch, a good operator. And what happened was he called us because he said he thinks someone was dumping on him because he has high ammonias in his system. Okay, he's only running half his plant, as you can see, because that's all he really needed to do. But, with high ammonias, maybe he needed to bring the other side online. But so the first thing we said was, well, is your DO probe good? Is it calibrated right? He goes, yeah. We measured plenty of DO. And then, so we went and we put some data logging equipment in. We have these data loggers that measure DO and ORP and pH and conductivity and temperature. It was summertime. We put one in the raw in hopes to find some sort of low ORP flow coming in that might indicate somebody dumping. And we put one in the oxidation ditch. But here's what we found when we came back a week later and downloaded the probes. This was the DO profile in the oxidation ditch. And what you see is this is 2 days in May, from midnight to midnight. And what you see is about midnight, the DO climbs because there's not much flow coming in, and it goes up to around 4 on the first day. But then around, I don't know, maybe 8:30, well, by 9 o'clock, or about around 7 o'clock, it starts to go down when the morning flush comes in. By around 9 o'clock, it drops less than 2 milligrams per liter of DO. And by, I don't know, maybe 11 o'clock, there were less than 1 milligram per liter of DO. And it stayed that way, less than 1, until almost 10 o'clock at night, when it starts to recover and starts increasing again. Within the next day, the same thing happens. What happened was the operator was a creature of habit. He would come in the morning at 7 o'clock, he would start coffee in the lab, and he would go out and make his rounds with his DO probe. So he was going out around and checking DO in the plant, you know, sometime between 7 and 8 in the morning every morning, and he had plenty of DO. Well, what he thought was he had plenty of DO all day long. But since he was only measuring DO at the same time as he always did, he missed the whole picture. And only when we put a data logging DO probe in and got this plot did he realize what was going on. Okay? So maybe here's another way. And so what he did was he actually had a second rotor in the oxidation ditch, and he got a timer for it, and he kicked the second rotor on around 8 o'clock in the morning and kicked it off about 10 o'clock at night, and he hasn't had an ammonia violation since. Box 10, okay, if you do have low DO, you need to increase the air supply. It's funny, if you don't have good screening and you get a lot of rags and stuff in the plant, they always seem to wrap themselves around diffusers. So sometimes you have to drain a tank and get all the rags, this is an extreme example, off the diffusers, because they will impact the amount of air being transferred to the mixed liquor. Okay? Maybe you turn the air way down in the winter. You had a timer and you turn the air way down in the winter time, and you forgot to give it more air in the summertime when oxygen is less soluble in the mixed liquor. So check your timers. You could check your system loading. You might have to send that out to do a BOD test and see if you have an increase in loading or not. But it could be a mechanical issue too. It could be blowers, or it could be diffusers. Here is a diffuser for a wastewater treatment plant. As you can see, the holes in the pipe are clogged, very clogged. This plant had been out of compliance for DO or for ammonia for, I don't know, a couple of years. And it's around a lake, a recreational lake, and they were wanting to build some new houses, but you can't send new flows to a plant that's out of compliance. So they called us because they really wanted to have these new houses being built. And we pulled them, and this is what we found. When we took them apart to clean them, we found that the diffusers were full of sludge. Well, sludge and grit and everything else that accumulates. Huh, that's interesting. So we cleaned everything up, put it back, and by the next morning, the plant was in compliance for ammonia because the air distribution was so much better. Okay. There's the timer again. Maybe you didn't have the blower running as much as it should in the summertime because you reduced it in the wintertime. Okay? Okay, so if it's not, let's see here, your ammonias are high in the aeration tank, it's not too cold, you have enough alkalinity, you have enough dissolved oxygen, maybe you don't have enough mass, okay? This is box 9. Box 9 says, is your aeration tank effluent centrifuge spin less than 4%? Okay? Centrifuge spin. Not everybody knows how to use one of these. These are awesome tools. In 15 minutes, you can figure out where your solids are. Okay? The bacteria need to be in the aeration tank in order to do their job. Oftentimes, the aeration tank centrifuge spin is low, but the clarifier centrifuge spin is really high, okay, because all the solids had been pushed to the clarifier and it wasn't being returned effectively. So in 15 minutes, there's 6 centrifuge tubes. So what I normally do is take 2 from the aeration tank, I do a core sample and stick that into a bucket and spin that, and then I take a return sludge spin. So I have 6 samples and spin them down. And if typically what we find is if a aeration tank contents mixed liquor is someplace in the 2 to 4% range, you probably have enough bacteria. If it's less than 2, it may not have enough bacteria to do the job. So if your centrifuge spin is very low, you might not have enough in the aeration tank to do the conversion process. Okay? There's the picture of the centrifuge spin. You go out and you get a sample and you fill your centrifuge tube up to 100%. You fill all 6 tubes, or else the centrifuges tend to walk off a countertop, because if it's it has to be balanced because it spins at about 5,000 RPMs. And after 15 minutes, all the sludge goes to the bottom of the tube. And the tube has gradations on it, so you can read what the percent volume of solids are in the sample. So this one looks like it's about 5, 6, about 7 or 8. It's about 7 or 8 spin. That's a lot of solids in the aeration tank. Okay? So if you don't have enough spin, if your spin is way lower than 2, then you need to decrease wasting, okay, to increase biomass in your aeration tank. If it's really cold out, the bacteria work slower, so you might need more bacteria to do the job. Or if you have an increase in load coming into your plant, you might need more mass. But you can spin these down in a centrifuge, and in 15 minutes, you can see how much mass is in your aeration tank. That's much better. In 20 years, I've never done a mixed liquor suspended solids test. I've always used a centrifuge. And the nice thing about the centrifuge is you can run chemistry on the clear stuff on top. Okay, so if it's warm enough, if you have enough alkalinity, you have enough dissolved oxygen, you have enough mass, it may be that maybe you just don't have enough tank capacity. Now, this test is not one I perform very often, and I don't really like it because you can't get the data you need for this test, organic loading rate test, from the tools that we have. But we felt that we had to do it because it could be that the plant is just overloaded. So what you do is you look at the organic loading, and it's the pounds per day per 1,000 cubic feet of tankage. Okay? So you take the CBOD or BOD to get the pounds, you take BOD or CBOD and multiply it by the flow rate in million gallons and multiply that by 8.34, and that will give you the amount of pounds per day that you have coming into the plant. And then you take the length times the width times the water depth. That gives you the cubic feet of aeration tank that you have. And then you divide that by 1,000, and that will tell you how many thousands of cubic feet you have of aeration tank. Then you take the pounds per day, divide it by the thousands of cubic feet that you have, and the standard is you should be less than 15 pounds per day per 1,000 cubic feet of aeration tank. Okay? So let's do the test. So let's say this is for a slightly bigger plant. You have two tanks, two aeration tanks, and they're 56 feet by 12 feet by 15 feet water depth. Okay? The aeration tank environment is you have 0.135 million gallons per day of flow at 218 milligrams per liter of BOD. You figure out the pounds, and that comes to 245 pounds per day of BOD. You figure out what the capacity of your tankage is in thousands of cubic feet. So you take two tanks times 56 times 12 times 15, divide that by 1,000, and that gives you 20.1 thousands of cubic feet of aeration tank. You take the top number, divide it by the bottom number, pounds per day divided by the thousands of cubic feet, and that gives you 12.2 pounds per day per 1,000 cubic feet of tank capacity. So this example would be within its design capacity, okay? Because it's less than 15 pounds per day per 1,000 cubic feet. Okay, so if it is beyond the design capacity, you need to increase capacity, okay, or decrease the flow, okay? So one thing that may be causing it to be overwhelmed might be flow equalization. So at given points during the day, different times during the day, you might have so much flow coming in that it exceeds the design parameters of the aeration tank. Okay, look at this flow meter chart recorder. That's a 7-day chart recorder. Looks like it's been pegged on all but about 2 or 3 days. Okay, so maybe you need to check your pump station, what they pump at. See if you have I&I. I think this flow chart here, I think it was draining the river that was close by. That would cause a capacity issue. Here is a design problem with the flow EQ tank. Now normally what happens is, what you see here are the discharges from the EQ basin, and it goes into the splitter box. You have a very narrow weir that goes forward into the treatment plant, and there's supposed to be a really broad weir behind those pump discharges that flows back into the EQ basin. But in this example, the plate wasn't cut as a weir. All it did was send all the flow forward. So the flow was beyond its design hydraulic capacity every time the pump kicked on. Okay, not good. And again, here's a flow problem with a concrete block in the flow channel again. What they saw was that one side got a lot of flow, was beyond its flow. It was a 2-train system, and one tank was hydraulically overloaded with flow, while the other tank was way under capacity. Well, when those flows come back together in the clarifier, the side that was hydraulically overloaded would not treat very well. The side that was under capacity would treat just fine, but there was so much more water not being treated than being treated that when the flows come back together again, it resulted in a violation. So flow splitting can cause an apparent capacity issue. Okay? Or if all else fails, you might just have to build some more plant. Okay, so if it isn't water temperature causing conversion issues, you have plenty of alkalinity, you have enough DO, you have enough mass in the system, and your organic loading rate is below the design capacity of your plant, then maybe, just maybe, you might have a toxicity issue. Now, operators frequently like to blame somebody dumping on them something toxic and killing their biology. In 20 years of troubleshooting plants, I've seen that probably less than a handful of times coming from outside the fence of someone dumping. It does happen, but it's not as common as you might think. Normally what we see are inside the fence issues. And normally what it is, it's high ammonias being discharged from processes inside the fence to the aeration tank, and the alkalinity drops out, and you quit nitrifying because there's no carbon provided by the alkalinity for the nitrifying bacteria. So one major component or one major problem for high ammonias is digester supernatant. Both aerobic digesters and anaerobic digesters. Anaerobic digesters always have high ammonias being discharged, and if you're processing it or decanting the digester, you're going to have probably high ammonias. Now, aerobic digesters shouldn't have a lot of ammonia unless, one, there's no alkalinity in it because you aerate it 24/7 and all the alkalinity gets used up, and so you keep wasting waste sludge in there, and if it's not being converted, it will start breaking down and releasing ammonia. It could be that you have so much solids in your digester that when you turn it off to supernate it to get more room, you have to leave the digester off for a couple of days or longer. And what happens after about overnight leaving the digester off is the solids will start breaking down and dying, and they will release ammonia into the water column. And then you decant that high ammonia back into your aeration tank, and then you run out of alkalinity, pH drops, you quit getting treatment, and you have a toxicity violation due to shooting yourself in the foot. Okay? Other sources, there are some external sources of toxicity. Force mains. If you have a really long, low-flow force main, the wastewater in there could go very septic, and when it comes to the plant, it could all the solids could be breaking down and have huge amounts of ammonia in it. Septage receiving stations, you never know what you're getting when you're taking in septage. Sometimes it might be just fine, sometimes it might be an issue. You should always sample the septage before it's dumped, and then just don't let them know if you're testing it or not. And if you see a problem, then you can test it and find out what was in it. And also look for color, corrosion, and odor. Right here is a manhole from a plant. It was another small diameter gravity system where all of the houses had septic tanks, and then the septic tank effluent would go into the collection system. Well, at the very end of the collection system was a honey manufacturer. Okay, and they had a high organic load going into a septic tank. And the other problem was that the water in the community, it was well water in the community, and it had a lot of sulfur in it. So you put a high organic load, sulfur-filled water into a septic tank, you get hydrogen sulfide. And hydrogen sulfide into a collection system forms sulfuric acid, and it corroded almost everything down the main line of the sewer system in this small town, and it corroded the plant as well. So anyway, so when treatment plant operators say that they are having toxicity issues, I always urge them to look inside the fence first, and that's where I would look first. And then you can start looking outside the fence. But outside the fence is hard to cover sometimes. One thing you can do, this is a simple toxicity test for nitrogen. It's a nitrogen uptake test. And in this particular example, we were looking at leachate from a landfill going into a small town's treatment system. So what we did was we got mixed liquor from the treatment plant in 1, 2, 3, and 4. We put different combinations of raw wastewater and leachate, added that, and then we got the control as a well nitrifying treatment plant, and we added leachate to that as well. And then we started aerating it, and every half an hour we would run an alkalinity test and an ammonia test to see if the ammonia was taking up, if the ammonia concentration would be going down, or if it was a straight horizontal line, or if it even went up. Well, here's what we found. What we found was we had two concentrations where the initial ammonia concentration was around 20 milligrams per liter and in 2 of the bottles, and then 3 of the bottles it was 40 milligrams per liter. And what we found was the leachate was not toxic at all to the treatment plant. It took a little more time, but because of the high load, but it treated it just fine, as evidenced by the downward sloping line versus time of the ammonia concentration. Okay, so for complete oxidation of ammonia to nitrate, for the 20 milligrams per liter, it took around 6.5 hours to 7 hours. For the 40 milligrams per liter, it took about 11.5 to 12 hours. Okay, works just fine. Wasn't toxic at all. Just took time. So there we go. That's the activated sludge process control and process control and troubleshooting chart. We've gone through the entire chart. I think my next slide will have a link to it on the Ohio EPA website. I urge you to download it, the chart and the manual. The manual is about 56 pages, so you might not want to print it out, but you could save an electronic copy and have it with you. So that is my conversion, part 1 of the activated sludge process control and troubleshooting chart and manual.
Thank you very much,
I think
John.
we're going to open it up to questions.
Yes, thank you very much, John, for your presentation. And before we start with questions, I want to urge folks to look for part 2 of John's presentation, which was recorded on November 13th and is posted as well. So, John, we do have a few questions.
Okay.
So let me run through them. And one was a compliment on the flow chart, but saying it would benefit from an outdate for designs for biological nutrient reduction that incorporate anaerobic and/or anoxic zones. This is fairly common in small mechanical plants constructed in the last 5 years.
Yeah, well, actually, that's the next presentation or the next webinar, isn't it?
Yeah, right. Okay, so we'll let that one go. Another
Okay.
one was, don't you get some heat benefit from compressed air?
That's a good question. I don't think you really do because, okay, here's my reason for that. If you look at how a refrigerator works, it compresses gas and the compressor gets really hot. But when the gas escapes through the nozzle, it refrigerates. It cools temperature down, and that's how a refrigerator works. And I'm thinking an aeration tank, even though we don't have those kind of pressure nozzles like a refrigerator might have, I'm thinking the pipes where the compressed air is warm up, but when it's released into the aeration tank, I don't think it adds very much heat.
Okay, the next one, is this flowchart and process control available on an app or online?
Again, if you look at my somewhat complicated Ohio EPA website, or you send me an email and I'll send you the links to it. It's available as a download. I have it on my phone. It's not really an app, but it is available online and you can download it and you can have it with you on your phone. It's a little small to see on the phone, but it works. But maybe what you could do is print out the chart, have the manual on your phone, and you could bring it up if you needed to.
Maybe, John, we'll put that on a national wish list in terms of converting this. Maybe that's something we should talk about.
Yeah, maybe
All right.
maybe US EPA can do an app with it. How's that?
Okay. Well, I'll throw that out there if the opportunity raises itself.
Okay.
And the next question is, what causes heavy buildup of scum in the scum baffle? What can be the causes? I guess it's causes of heavy buildup in scum baffle, question mark. Are you there, John? Okay. I think we've lost connection with John somehow. Is he still online?
He's still online.
Okay. Did you hit mute by chance, John?
Everything's showing him.
Okay. Well, I'm gonna again thank John for his very cogent presentation. I think we're gonna go ahead and stop the recording now. Anyway, thank you for listening, and please see our additional webinars that are also on the website. Thank you.